Previously, we've learned about the single variable functions. It's a type of the function which is taking a scalar as an input, and it does some operations with the scalar, and it's going to give us another scalar as output. So today we're going to talk about the multivariable functions. For example, it's going to take a vector x and y, it does some operations with this vector, and it's going to give us another scalar. For example, a line, right? Or as a curve. So where x is going to be independent and y is going to be dependent. What does it mean? It means that depending on which value for the x we choose, the height of this curve, it's going to be different, right? It's going to be f of x here. So we can choose any value for the x here, and this is we decide to choose this because x is independent, and the value for the y is going to be dependent on the value of the x. So the typical graph of the two variable function looks like this. It's going to be a surface basically. So this might be a graph of the temperature function, which is going to depend on the two variables and x direction and in y direction, or it might depend on the position and the time, right? So depending on which time we choose and depending on which position we choose, we might have different temperature. So what we're interested in is to know the derivatives of the temperature or this kind of functions. So in order to do this, let's start with the derivative of the single variable functions. So we're going to talk about the derivative of the distance function. So let's say this green curve is a distance function, which is going to tell us the distance passed through until some point of the time, right? So let's say at some point of the time t1, the distance passed through is s of t1. At some point t2, the distance passed through is s of t2, right? Then the distance between the points s1 t1 and t2, it's going to be s of t2 minus s of t1. So what we're interested in is the rate of change of the distance between this t time. How much the distance have changed between this t time. In order to do this, we need to divide the difference of the distance, right? The distance we pass through with this car divided to the difference of the time. So this is going to be the rate of change of the distance with respect to the time between t1 and t2. So sometimes it is interested for us to know the instant rate of change of the distance with respect to the time. Basically, how much the distance is changing at a given point. In order to do this, we are going to take a small displacement on the time, right? T, the some time, plus some h, minus the distance at the time, divided to the t plus h minus the t. Right? The similar thing what we did before, right? We are going to take the rate of change. So here we take the rate of change of the distance between the tt and t1, and here we're taking the rate of change of the distance between the t plus h and the t. So if it take the limit when h goes to the 0, basically, if this t points t plus h and t are going to be really close to each other, then this is going to be the instant rate of change. And actually we denoted this as the derivative of the distance with respect to the time, which is nothing else as the velocity, right? So the rate of change of the distance with respect to the time is the velocity. So now when we are talking about the two variable functions, we can just take the derivatives like this. So basically, let's say we are given a function of the temperature that's going to depend on the position x and on the time. So graphically, it looks like this. So depending on which time we choose and which position we choose, we might have different temperature, right? For example, let's say at the time to be equal to the 0, the temperature curve looks like this. When the time is equal to the 1, the temperature curve like this, and in between of them, it might be different lines and so on. So the temperature function now is going to be a surface, right? So now we would be interested to know how much the temperature has been changed with respect to the time or with respect to the position. So let's choose one position on the x, and let's measure the temperature at 12. And let's choose the same position, x0, let's say, and let's measure the temperature at 3 p.m. So now what I would like to know is how much the temperature has been changed with respect to the time. In order to do this, what I'm going to do is I would like to find the temperature at the x0 and the time. T0 is going to be 12. So n at the 3 p.m., sorry, T0 plus the h minus the temperature at the x0 and T0, right? I would like to measure the temperature at 3 p.m., then I would like to measure the temperature at 12 p.m. at the same position. Then I would like to find the difference. And when I divide this to the difference on the time, which is the h, right? Then this is going to give me the rate of change of the temperature at the same point with respect to the time. So please note here, I'm taking the position as a fixed, right, as a constant, because I'm measuring the rate of change of the temperature at the same position. So when I take the limit of h goes to the 0, this is going to be the instant rate of change of the temperature with respect to the time, right? This is similar to what we did before. So at the same time, we can measure the temperature at 12 p.m. in the different positions, right? So let's measure the temperature at x0. And at the same time at 12, we can measure the temperature at the x0 plus the h, right? Now I would be interested to know how much the temperature is changing at the same time if I go through the x line, right? If I go to the different position. So the temperature at the x0 plus h and the t0 minus the temperature at x0 and t0, I'm measuring the temperature. Please note that I'm measuring the temperature at the same time, right? But in the different positions. Divided to the h, it's going to give me the rate of change of the temperature with respect to the position. So when I take the limit, when h goes to the 0, this is going to be the instant rate of change of the temperature with respect to the position. So previously, we defined the rate of change of the distance with respect to the time, right? Now we defined the rate of change of the temperature with respect to the time as one function, and we can define at the same time the rate of change of the temperature with respect to the position as a different function. So we are going to define this t items as the partial derivatives. So this is going to be partial derivative of the temperature with respect to the time, and this is going to be the partial derivative of the temperature with respect to the position, right? So please note that when we are taking the partial derivative of the temperature with respect to the time, the position is fixed as the constant, right? And when we are taking the partial derivative of the temperature with respect to the position, the time is fixed. The time is a constant. So let's do an example in order to understand how we need to take the derivative from the real function technically. So let's say we are given a multivariable function in the form of x cubed plus x squared y minus t y squared. What we need to do is we need to find the partial derivative of the f with respect to the x at the point t and 1. And we need to find the partial derivative of the f with respect to the y at the point t and 1. Okay, so in order to find the partial derivative of the f with respect to the x, as before. So when we take the derivative of the f, t, with respect to the time, the position is fixed. Position is a constant. Here as well. So when we take the derivative, partial derivative of the function with respect to the x, y is fixed, right? Y is the constant. So that is why the derivative of the x cubed is going to be 3x squared, and derivative of the x squared it's going to be just some constant y multiplied to the x squared, right? I look to this function and I see that y is the constant because y is fixed, right? I'm not changing the y, I'm just changing the values for the x. It's going to be tx multiplied to the y minus the derivative of the t y squared. It's going to be simply 0 because I'm taking the derivative with respect to the x. is 0. Now I need to evaluate this function at the t and 1. I'm going to substitute the x was a t. It's going to be t multiplied to the 4 plus t multiplied to the t. And I'm going to substitute the y was the 1 multiplied to the 1. It's going to be 12 plus 4, which is 16. So now when we are going to take the derivative of the function with respect to the y, I need to look into this function and see that x is going to be a constant. X is fixed, right? So do you remember when we took the derivative of the temperature with respect to the position, the time was fixed, right? We measured the temperature at the two different positions at the same time. So the same is here. So x is fixed. X is a constant. So that is why when we take a derivative of this function with respect to the y, so this is going to be 0 plus this is going to be constant square, right? Multiplied to the derivative of the y, which is 1, minus the derivative of the ty squared is going to be t multiplied to the ty, right? And when we measure this at the point t and 1, I'm going to substitute the x was the t, it's going to be 4, minus t multiplied to the t multiplied to the 1, right? It's going to be simply 0. So this is how we need to take the derivative, the partial derivatives of the functions with respect to, say, one or another variable.